Today we will start with a problem. There is a problem which is given in your book. It's an example. I will read it. Three identical point masses are fixed symmetrically on the periphery of a circle. What they have said is, okay, so there is a circle. It's an interesting problem. Okay, this is a circle. Three identical point masses. What is that? Point masses. Three identical point masses. Let us call it as M. Okay. Are fixed symmetrically on the periphery. Symmetric means they all make a equal angle at the center. Okay, so something like this. So the 3 point masses are fixed like this here, and they are equal masses M. Okay. Obtain the resultant gravitational force on any point mass M. Point mass M at the center of the circle. Okay, center of the circle. Extend this idea to more than 3 identical masses symmetrically located on the periphery. How far you can extend this concept? Understand? Got the question? So first you do for 3 bodies, then you extend it for more bodies which are symmetrically placed, 4, 5, 6, 10. Then how far you can go? Can you get anything out of it? Okay. So it is simple. So of course the gravitational force is attractive force. So these masses are fixed. They won't move. So only this attraction is going to pull this mass towards the center. Okay. Can you just usually say what will happen? Will the mass move anywhere else? No. It will be stationary because all forces will cancel each other, right? We have to show it now. How we are going to show it? So this is one direction of the force, and let this be the another direction of the force. Let this be the other direction of force, right? The attractive forces. So, and what will be the magnitude of the force? This, what will be this distance?
Radius.
Radius, right? Let us call the radius. So, what is the magnitude of the force? Tell me. The force. Let me call this as F1, F2, F3. Let us call this as object 1, 2, 3. Mass, point mass 1, point mass 3. Okay. The force on M by the point mass, on M by M at a distance. How much? Tell me. R. R will be, what is that? All forces are same. Your distance are same, the mass are same. F1 will be equal to F2 be equal to F3, and that will be equal to GMM by R square. Okay, so all these forces are equal. Now we have to say, will the mass in the center, will it move or will it be stationary? Simple. The way to show it is, you take, so these two forces will have a component force along this direction. Correct? And if you show this force is equal to this force, then they both cancel. Huh? So you show it for only once. The same you can do it because all identical, symmetrical. This will be same for here. This will be same for here. So you have to just show one. So which you can use? What property you can use? These all are vectors. This force is a vector. So if the resultant vector, na, you have to go for vector addition. Am I right? So let me draw this. I'm going to draw this one only. Okay. So let me draw this as. Okay. So let me rotate it like this, so that it will be easier for you to understand. So this is. Let me call this as O, A, B. And maybe, okay, so let me write O, and this is your A, and this is B. Can you tell me what is the angle?
60 degrees. No,
60 degree.
360 degrees.
Huh?
360 degrees.
This is 360 degree.
The whole thing is 360 degrees.
Divided by
360
3.
divided by 3.
120 degree. Correct. So this is 120 degree. You should know the angle 120 degree. Am I right? So this is the vector. Two vectors. Can you tell me whether the vector length will be equal?
Yes.
Because the force is same. Correct. So let me call this as F. This is also F. Magnitude is F. And now we want to find out the resultant vector. Am I right? So all what you do the parallelogram. Parallelogram law of addition. Am I right? The same direction here, the same direction here, and this will be the resultant vector. So let us call this is a resultant vector R. Okay. And what we have to find out? We have to find out is angle also. You remember the angle is alpha. We have to find out. That's a formula. Okay. So, right. The resultant vector R let R be the resultant vector due to OA and OB. Am I right? So what is the magnitude of R? You remember that? And R will be what? We write it R square. If you remember, R square will be what? The resultant vector. Oh my goodness, I written the same symbol. Okay, so let me call this as at a distance small r. Okay, the radius I am using small r. R square. Okay, so what is the resultant vector? You remember? What will be? OA square plus OB square plus 2, correct, OA into OB into cos theta. Theta is the angle between these two. Correct? This is 120 degree. Okay, now tell me. So what is OA square? OA square is F square. F square. Correct. F square plus F square plus 2F square cos 120 degree. Do you know what is cos 120 degree? Minus half. You should remember all those things. Okay. So cos 120 degree is equal to what? Minus half. So this is into minus 1 by 2. So this goes off. So minus F square, this will be F square. Therefore, R will be what? Be F. Okay. So this magnitude of this vector is going to be F. Okay, this way you are getting the vector in this direction. Now we have to find out the angle also. This angle alpha. You remember that formula for angle?
Alpha equal to tan minus.
And that is a tan alpha. Tan alpha equal to OA or no, I think it's OB you have to do it. Yes. OB sin theta divided by 1 plus OA cos theta. That's right? Yeah. Not 1 plus. I made a mistake. OB plus, yeah. No. OB. OA plus OB cos theta. Okay? Correct. Yeah. Yes. Okay. Tell me, what is OB? OB is F. So, F sin 120 divided by F plus F cos 120. Right? All the F will cancel. So, we are going to get sin 120 divided by 1 plus cos 120. Okay, what is cos 120? Minus half. So, this is going to become plus half, right? Sin 120. What will be sin 120? So, tell how much this will be. Sin 120 is how much? Okay, sin 120. Sine 120 is root 3 by 2, right? 3 by 2 and cos 120 is minus half. Is that correct? Oh, sorry, 1 minus half. Na? Okay, so this will become half. Okay, so it's eventually becoming root of 3. Correct? So can you tell me if tan alpha equal to root of 3, what should be alpha? Says. So we got the alpha also. Alpha equal to 60 degrees. So now you tell me what is this angle? So therefore, this angle is 60 degree. So this will be exactly opposite, right? So of course, so the resultant force, therefore, the resultant force is equal and opposite to the third mass, to F3, correct? To F3. To F3. Therefore, M will be at rest. Cancels. Okay. So this is a simpler way to prove it. Okay, in your book they have proved in a different way. Okay, I will show you how they have proved it in your book, how they have shown it in a book. Means this is more simpler because this is what you already read about it, right? All the vector additions and all. So I find this will be more easier. Okay, let me explain in a book what they have done. So what they have done in your book is, so they have not done all these things. So similar way, then we did for these two. So similarly, you can show all the resultant force will be opposite to the third force. Okay, the resultant force of two attractive forces, two masses will be opposite to the, equal and opposite to the force of the third mass. So therefore, it will be, the body will be at rest. Okay, in the book what they have done is, they have resolved this force, these two forces, okay, so into two components. Okay, that way also you can do. Pardon?
It should be like the between F2 and F1 and F2, that line is not correct. Okay, you're doing it now.
Yeah.
I thought you were drawing.
Yeah, I'm taking this vector. I'm going to, means you have to resolving a vector into perpendicular components. I'm resolving this vector into perpendicular component and this vector into perpendicular component. If I call this angle, this is equal to this. That means how much this angle will be? 60 degree. Am I right? Because total angle is 120, so it's 60 degree. So what will be this component? The vector due to this component. F1, this will be what? Along this angle. F1 cos 60. Am I right? Similarly here also F3 cos 60. And this is F1 sin 60. This will be F3 sin 60. F1 and F3 are equal. Therefore, these both cancels each other. Now let us take this one. F3 cos 60 plus F1 cos 60. So this is a total force, right? So what it will be? Tell me. So total force will be okay. Right. Okay. So total force will be, this F3 and F1 are equal. So the resultant total force F total will be F2. No. 2F cos 60. Correct? 2F cos 60. Correct? So 2F cos 60. Tell me, what is 2F cos 60? 1 by 2. So it's equal to what? F. So of course. So we are getting F, and that cancels with the opposite way. This is the way in your book they have shown. Okay. So we can show it to the vector addition also. Okay. All right. Yeah. Now coming to the second part. If we keep increasing the masses. So now this is 3. If I keep 4 masses, they all has to be kept symmetrically. How will I keep it? So let us draw it. How the 4 masses will be kept symmetric? Tell me. So we have the circle.
Split the angle into 4 parts.
Right. Yes. How much it will be?
If you
This is just diagonal opposite, na?
uh,
4, correct?
90.
90. So tell me now. These are the 4 masses.
It will be the same, right?
Yeah, because opposite, they are equal opposite. Naturally, they all will cancel. Okay? And similarly, if you have 5, 360 divided by 5. Okay, again you can show for odd number, the resultant force will cancel the opposite forces. Okay, same way all the, so in a even number of masses is natural. The opposite force will be cancel each other, and the odd forces, the resultant force will cancel each other. Okay, therefore the body will be stationary. So now the question is, so you keep on increasing. Whatever you do, so either it's even or odd, the resultant force at the center is going to be 0. So if I add up infinite masses, symmetric, fully, if I fill the whole circle with mass, equal mass, what will be the gravity at the center? 0, because everything cancels. Now I made it into a whole sphere, 3 dimension. What is the gravity at the center? 0. Okay, so that's what the problem is. Okay. Then there is a box in your book. This is about the unification of forces, and that's I told you also, right, earlier. See, what about Newton unified the terrestrial force and the celestial force? Yes, see, your Newton law of gravity and everything, he tried to bring all the forces. One sort of unification he did, Newton law of gravity and the Newton's laws of motion. So by this he was able to get a, because see, what is the acceleration due to gravity is your weight is mg, and we saw that mg is nothing, you get it from the Newton's law of gravitation. So that's how you unified these two terrestrial forces and the celestial forces. Then the experimental discoveries by Oersted and Faraday showed that, okay, this you can read it, you can just informations. Okay, so what they showed is, I told you also, magnetic and electric and magnetic phenomena are generally inseparable. They both are same. Okay, and leading to what is called as the electromagnetic phenomena. That's EM phenomena. Okay, and then the Maxwell showed electromagnetism and optics were unified. Maxwell showed your light is nothing but an electromagnetic wave. Okay, this all you will learn it later on in higher classes. So that's why they unified the optics with the electromagnetic wave. Okay, and then come Einstein attempted. This is one of the Einstein spent almost his entire life in trying to, after his relativity, to try to unify gravity and electromagnetism. Is there any way to unify these forces? Okay. So, but he could never succeed. So, and this force was unified. Electromagnetic force and the weak nuclear force. You remember there are two weak and strong forces. Electromagnetic and weak force, they were unified by Abdus Salam and Weinberg and one more. I don't remember the name often. Okay, so these 3 Nobel artists, they got Nobel Prize for that. Okay, so they unified the electromagnetism and the weak nuclear force. Strong is still open. That's for you to get a Nobel Prize. Okay, you can unify and get a Nobel Prize. Okay, fine. So this is the unification of forces. This is one of a very advanced topic. Okay, good. So, and then now we have the string theory. With string theory, they say all the forces can be unified. But yes, there are many critics for that also. Anyway, we don't know for that. Fine. And now we are, okay, next what we are going to see is, we discuss about it. 2 types of forces, contact and non-contact forces. Am I right? What I said about contact forces? Well, there's the 2 bodies are contact. Okay, I am standing on the ground. There's this force a contact force or non-contact force? Why? I'm flying on the air or I'm on the ground? Right. So it's a contact. Contact. Okay. So everything. So you hit a carom coin. It go and hit. These are the contact forces. Okay. Non-contact force is what? Orbit of moon around the earth. Okay. There's a force acting, but are they contacting each other? No. Okay. Or your planets. or a magnets, two magnets. Okay, repulsion of two magnets. So they won't be contact, but there will be force acting on it. Okay. Interestingly, all contact. Now you know about the types of forces, right? Gravitational, electromagnetic, strong, and weak. Okay. Can you tell me all these contact forces are basically due to one type of force? Gravitational force, moon and earth is in contact.
Okay, no, it's not in contact. Okay, contact force, right?
Ah.
Contact force would be electromagnetic force.
Correct. Why? Because why am I sticking on the earth? Okay, I would have merged into one, one. Okay, because there are my molecules are there. They are not letting me to stuck together. They are opposing. They are giving the reactive force, and I am standing like that. Okay, so if you actually see, all contact forces are basically EM in nature, electromagnetic in nature. Okay, maybe anything. If suppose you take a you hit a punching ball or something, it gets deformed and then pushes you back. This is all electromagnetic, right? Because they all atomic structure, you are deforming and then it realigns itself and then pushes you back. So these all are basically electromagnetic forces. Okay, so all contact forces are basically electromagnetic in nature. And other forces, mostly gravitational force, and okay, gravitational force is the cause for here, but it's not necessarily be a contact force. Okay. And the interesting thing is, yes, okay, then when you have a contact force and then there's non-contact forces. So when you have a contact force, then you can define what they call, there are two forces: normal reaction and what they call the parallel or tangential component. Normal component, tangential component, parallel component. This basically came from an object moving in a circle. We should do that. Okay. So for example, so I know in a book it is written in a very confused way. I will explain you what it is in a simpler. What I say is, if a normal, okay, let us take the Earth. That would be interesting one to see. Oops, I spoiled the shape of the Earth. Okay, so let me draw it neatly. Okay, so we are having Earth. Still not bad. Okay, so, and there is an object. Okay, so, and there is a gravity. So you are, suppose if this is you, your gravity is attracting a force. Okay, so I am exerting a force on the ground because of the gravity. Now will the ground be idle? Ground will give me opposite, because every action has an equal and opposite reaction. So this will give me an opposite. Correct? This is given by the ground on me. So that's what you call as your normal reaction. Okay, what they call is normal reaction or normal force. So what you call this as your normal force. Okay, this is what when the body is in stationary. Now you want to move this body. What are you going to do? Yeah, tangentially you have to give a force component. Okay, so then what happens? You are going to pull it tangentially. Okay, then there is a frictional. The body will have some irregularities in the bottom. So those irregularities, because these are atoms only, right? They all are contact. They are not letting you. So they will give you an opposite reaction. Okay, and this is what you call as a tangential component. Or parallel. Parallel component. Yeah, if you take your surface to be a parallel, you are on Earth. It's actually a sphere. Okay, but now I won't see I don't see the Earth is curved by sitting on a point. For me, everything is parallel, right? If I want to move, for me the surface what my home is plane, but it is actually not, because Earth is spherical. Okay, so in a small region I can see it's a plane. There the force will be parallel. Am I right? That's why it's called a parallel component. When you see it in a complete circle, it becomes a tangential. You got it? Okay. So I'll read in a book, it's written in a very slightly confusing way. Okay, see, the point is, quite often we call it, okay, two objects in contact while exerting mutual force try to push each other away. This one. I am pushing the earth down and the earth is pushing me up. Okay, that's what it says. Okay, quite often we call it as a normal reaction force, normal reaction force, or normal force. While standing on a table, we push the table away from us downwards, and the table pushes away from it upward. Okay, both being equal in magnitude and acting along the same normal line. Am I right? So that's a normal force. Force of friction is also a contact force, correct? Because when you roll it also there's a contact. This is also contact force. When you're rolling it, when you're pulling it, dragging it, this is also contact, because there what happened, what is going to stop, you can't drag it easily. But there's a frictional force is there that won't let you to drag. Okay, so the force of friction is also a contact force that arises whenever there's a relative motion. You got it? Or tendency of relative motion, not necessarily relative motion. You may not roll, you just pull. If the force you have applied is lesser than the frictional force, of course, then you won't be able to pull. I give you a big log, okay, big rock, okay, I ask you to go and tie the Elephanta cave, that one big rock, and ask you to pull. Will you be able to pull? You have applied a force, okay, but there the frictional force, everything is so high, you don't move. In that case, what happened? That's what? Whenever there is a relative motion or tendency of relative motion, okay, the tendency of relative motion between the surfaces in contact. Okay, this is the parallel or tangential component, we call it as, okay, component of the reaction force. Yeah, actually I made a, I should have drawn like this. This is, okay, I would say this is, suppose if you are pulling here, let me put the colors. Okay, yeah, so if you are pulling here, so you haven't frictional force, which is giving opposite component, right? This is what you call as your parallel or tangential. Again, if you are pulling here, the force will be opposite side. It's opposite reaction force. These are reaction force. Okay. In this case, the molecules of the surface in contact, okay, which have developed a certain equilibrium, okay, are required to be separated, because you have to separate them out. So that's what your this is all about your contact and contact and non-contact forces. This is only contact forces. Non-contact force I told you, na? Means wherever there is no contact. Okay, fine, that's one. And then next important thing comes, that's quite very interesting. That is, I will write about it. That is real and pseudo forces. I explained you. Remember that? Real and pseudo forces. Why this is important is, so what Newton's laws of motion says is, if there is an acceleration, then there has to be a force. Okay, that's the law says. Okay, if there is an acceleration, there has to be a force. And now, then we saw about inertial frames. We also said the inertial frames satisfy the Newton's laws of motion. Okay, so now suppose we have a non-inertial frame. Let us take a simple non-inertial frame. You are on a lift. You got on a lift. Lift is at rest. You press the button. Say go for 20th floor. The lift start moving. Okay, and initially you are at rest. Suppose think of a situation, the lift is completely blackened. You can't see anything outside, or the lift is a big spacecraft kind of thing. Okay, where you can't see anything. You can't see anything outside. You live in that region. Okay, where you have everything is moving same. Now, if that big capsule or whatever you call, if that acts like a lift, it was there, suddenly it starts moving up. So what will you see? You are in a weighing machine. You may see you are 45 kgs. Now once it was at rest. Now when the capsule suddenly start moving up, you will see 45 kgs? No. Because of the force acceleration happened, you're going to, because from the rest you have moved up. So there's acceleration this capsule has done, happened. Okay, so therefore your weight is going to increase. So what do you see is, what it essentially means, you are having, there is another force. If you are inside, you won't realize anything. What you will see, suddenly you have put extra force on the weighing machine. Initially it was 45 kg, now it shows 50 kg because you applied extra force. But have you done? This is not a real force. You got it? There is no force because the frame, the earth. Okay, suppose the earth is there, you are standing. Your weight exactly on the top of the earth. Okay, so now earth is 45 kg. Now suddenly the earth starts moving up. Okay, so the backside someone put up a rocket and start moving up. Okay, then what happened? So then you will suddenly see the weight is increasing. But you are on the earth. You never know what is happening around because you can't see. The earth is just moving up. Okay, so then what you will feel? You feel that you are in a rest frame. Everything is, you assume you are in an inertial frame. Correct? Because you think you are in inertial frame. I am at rest. But you are not. Because your force you applied. There's nothing like a real force. There's some force you applied. Okay, so that force is called as a pseudo force because it's not a real force. Okay, this real force means this force cannot be categorized in the 4 types of force what we discussed. Am I right? This force doesn't belong to that. It's because of your frame. Because of your reference frame suddenly started accelerating. So you are experiencing a force. Okay, so that is not a real force of that 4 types. So you call that force as your pseudo force. Okay, and the pseudo force is not it's a real quantity because you measure it. Okay, and that is the one part pseudo force. The other interesting thing of this pseudo force is the same way. It's not necessarily you have to increase in more. You can decrease also. Suppose suddenly it's moving downwards. Then what happens? You feel your weight goes down from 45 to 40 you will become. Okay, but anyway you don't know because you are stationary. Okay, so this force was exerted. Okay, and the beauty is this force doesn't belong to any of these 4 types of force. And this, whatever the property you are seeing, can it be explained under the Newton's law of motion? No. See, for you, you will think that there is no force. You are at rest because I am at rest. Okay, I am at rest. So, of course, when I see I am at rest, the Newton's law of motion should act, should be correct. Okay, you assume because you don't know what is happening to your earth. Okay, you think I am at rest, everything as this, so the Newton's law of motion should be satisfied. But that is not true because your earth is moving down, suddenly accelerated. Okay, so during that period of acceleration, so then what happened? You have lost some less force you have put up, the force, your weight reduces. That means some force is acting. Okay, and that, and there is no, no essential acceleration or anything. That force, there was no force as such acting. Okay, it's all because of your the accelerated frame. Okay, that gives rise to this pseudo force. Okay, so this and this inertial frame. Now you associated yourself with a coordinate system. This coordinate system is an inertial or non-inertial frame? Non-inertial frame because it's accelerated. Okay, and now you think once it's accelerated, now after some time it starts reaching a constant velocity. Once after reaching a constant velocity, it will be a inertial frame. And when it stops also, suddenly it frames non-inertial. Okay, so any accelerated frame, in any accelerated frame is what you call as a non-inertial frame. In the non-inertial frame, you will have the pseudo forces. Any non-inertial frame will have the pseudo forces, and they are not a real force. Okay, but they are measurable force. They are measurable force, and these pseudo forces will happen. And if you are not taken this pseudo force into account, Newton's law of motion will not satisfy. Okay, so because Newton as it is, the Newton laws of motion doesn't work. So what you have to do? So you have to give an opposite, add a pseudo force component, should be cancelled. Then you can add up a deal with your Newton laws of motion. Okay, so that's what they have written here. Yeah, fine. Okay, the pseudo forces, the pseudo force does not mean imaginary because these are measurable with instruments. Okay, but just means non-real. They are not real forces. Okay, these forces are measured to be okay. Say something like if m is a mass, then what you call it is minus ma. Okay, hence a term minus ma added to the resultant force enables us to apply the Newton's law of motion to a non-inertial frame. You got it? So what happens? So now you are suddenly moving upwards. Okay, so there is a increase in. So your actual weight is mg. Okay, now since you are moving upwards, okay, so you have added an pseudo force, right? So that will be acceleration. Acceleration along this opposite to the direction of the gravity. Correct. So what you have to do, you have to minus ma. So when you take out this component, that means what happened? This is the component which has caused the acceleration. When you add up that component, then eventually you make into a inertial frame. Okay, this is the way. This is a very important concept. Now it looks, it's very simple, but when you are going in your higher studies, okay, when you go for relativity and general theory of relativity, this is a very important concept will come up. Okay, that you will read in higher classes. Fine. So this is what your pseudo force. Okay, and suppose if you're moving down, sorry, what I said is moving downwards. This is moving downwards.
That will be moving upwards, right?
Oh yeah, sorry, moving upwards. When you move downwards, it will be plus. Correct, because you're going along that same direction you're going. So it's for upward. And for downward, mg plus mva. I guess I written it correct. During upward motion, through upward acceleration, say we have mg plus ma. Yeah, okay. What you are saying is when you are in upward motion, what actually you face, what actual weight you face is, okay, I should written like that. When you upward motion, you have mg will be there plus acceleration. These are two components you will face, right, when you move upward. When in a downward, what you will find is mg minus ma. That's what they written it. Yeah, okay, minus ma. Okay, this is what they have written. Fine. So, and that's all about your real and pseudo forces. Okay. So tomorrow we will see about the tomorrow we will see about the conservative and non-conservative forces. Okay.